Okay, time to compare reduction to oxidation. We're going to start off with the same diagram, but think in the opposite direction this time. When you oxidize, you're going down this chart. Reduction is going from the bottom to the top. In this case, we're losing bonds between carbon and oxygen as things are reduced. And how those examples are done is what we'll work on stepwise next. When aldehydes and ketones are reversed, having that reduced, reverse of oxidation, essentially you're adding two hydrogens. And if you remember the first step of oxidation of an alcohol, you lost two hydrogens. So we're adding them back. The reagent that's commonly used for this is called sodium borohydride, which contains a hydrogen minus hydride ion, which is very infrequently encountered in other contexts, so this is kind of new most likely. And that hydride ion is attracted to the partial plus of a carbonyl. So the carbonyl has the partial plus on the carbon, and the hydride ion is attracted there. The second part of the reagent used for this reduction is going to be hydronium, namely aqueous acid. So if you put acid in water, it contains hydrogen ions that are correspondingly attracted to the negative end of the carbonyl. So the result is you're going to add two hydrogen atoms, one hydrogen ion, one hydride ion together comprise two hydrogen atoms. Not so big of a deal, but that's the idea that we're going to look for. So oxidation and reduction are the opposites of one another. So reducing an aldehyde or ketone, you'll always end up with an alcohol because you've added two hydrogens. And oxidation from an alcohol to an aldehyde or ketone, you're losing two hydrogens. Keep track of that. The reducing agent in either case is going to be the same kind of thing. And sodium borohydride, NaBH4, not that we're going to test you on it, but it's a nice way of remembering that there's lots of hydrogens present, that you can add hydrogens. And if you take an aldehyde, it's already got one carbon attached to it, or the aldehyde is only on one other carbon. And so the result is a primary alcohol every time, just the same as it was when you oxidized an alcohol to turn it into an aldehyde. And the ketone is on a secondary carbon, and so the result is a secondary alcohol. Not a big deal, but it helps us to keep track of what we're looking at when you're asked to decide how to do these reactions forward and reverse at times. Okay, so aldehydes always make primary alcohols. And remembering that the hydronium and sodium borohydride provide two places to yield hydrogen that's added to the carbonyl. Thinking in terms of the partial plus, partial minus of the carbonyl helps us to see that attraction. The ketones work the same way. It doesn't matter because you still have partial plus, partial minus on the carbonyl. The hydronium provides the hydrogen attracted to oxygen at the top, and the borohydride provides the hydrogen that's attracted to the carbon of the carbonyl every time. Nothing new, just to make sure we see how that's working. All right, so let's try some examples. Let's do reduction of these compounds and see if we can make sense of them. Well, we might even name them along the way because that wouldn't hurt. So we have 1, 2 carbons. Well, let's think about it. That one looks like an aldehyde. This one has CH, but then it's got CH3 on it 2 times. Oh, so maybe there's a hydrogen here and then a methyl and a methyl. So that looks like 3 carbons in the longest chain, so it would be propanal. Nice to name these things, just so you see where they're going. And then on the middle carbon is the methyl group, so it's 2-methyl propanal. All in one line if you fit it. If we put a reducing agent on here, we'll use the usual one. Things that provide hydrogens include the sodium borohydride and water. And we're going to turn the aldehyde into, every single time, a primary alcohol. So if we have 1, 2, 3 carbons, and the middle carbon is methyl group, those parts will not have changed. The only part that changes is the carbonyl. We'll still have a hydrogen. We have an oxygen that now has an extra hydrogen, and the second hydrogen will be on that first carbon as well. We would call this 2-methyl 1-propanol. Notice how similar the names are. No coincidence. The way you name these things is completely related. All right, so the next example is a little more interesting because you've got a benzene ring in it. It's always good to challenge those things with rings in them because they always make people hesitate. Let's try it. So metachloropenzaldehyde. So benzaldehyde means we're going to have a benzene ring, and you can't put an aldehyde in the ring, so you put it outside the ring. Meta means this position that's 2 away, so it's chloro. Does that have anything to do with this reaction? Nope, it's just there. And so put sodium borohydride on here. And hydronium, that means it happens in aqueous acid. That's what hydronium refers to. And the same thing. So we're going to go from an aldehyde again to a primary alcohol. And don't make it any trickier. Keep the rest of the compound exactly the same. We're not sure if we're going to name this one, so let's try it out and see what we think. The chlorine and the benzene ring look the same. And now instead of having the aldehyde, we'll keep one hydrogen. What was a double bond O as a carbonyl becomes an OH, and this becomes another hydrogen. This one have an odd name because it might be a phenylmethanol, but let's not say we want to name that one today. The third one on this slide, cyclopentanone. Pent, oh yeah, what does that mean? That should be 5, correct? And cyclopentanone, cyclo means put it in a ring. Pentanone means double bond O is on one of those corners of the ring. Nothing more to say, there's no other substituents. And this time we're going to say we'll use sodium borohydride and hydronium. You can write it above and below the arrows, whatever, that's the same idea. And will we do anything to the ring? Nope, the ring will stay the same. Now if we have a ketone, this time it better turn into a secondary alcohol, which I hope makes sense, because we're going to add hydrogen on 2 ends of this double bond. So we'll put one here, put one here. What does that give us? Well, we have now an OH. The extra hydrogen here doesn't have to be shown, but it's effectively where it's gone. I drew it up instead of down. It's all the same. And this would be cyclopentanol. That should make sense. I hope it does. All right, let's try another one. Whoa, you have to think about this. If you can do oxidation reduction, you can do them backwards and forwards. And it's a good challenge. So what compound might be reduced to give these corresponding alcohols? Compound A has an alcohol, and we have to decide what type of alcohol is it. Is it primary or secondary or tertiary? Well, if you look at this carbon, it's attached to 2 other carbons, so that makes this a secondary alcohol. And secondary alcohols are always produced from ketones. So we'll keep the rest of the compound the same. Put your 2 methyl groups here. Put the 2 methyl groups here. Whoops, I just said that the same thing. And now what compound is going to be reduced? It's going to be a ketone. So that would be cyclohexanone, as it turns out. Cyclohexanone with a dimethyl on it. Looks like 4, I better leave enough room. Dimethyl, I leave plenty of room. Cyclohexanone. So a ketone is always going to turn into a secondary alcohol. All right, let's do another one. See what we always name these when you can. Oh, I didn't name the alcohol. Well, I hope that looks similar to what you see there. All right, this compound here is another alcohol, and we have to identify what type of alcohol. It's a primary alcohol. It's attached to 1 other carbon, that's it. And so a primary alcohol is always going to be produced from an aldehyde, not a ketone. And the rest of this compound the carbon chain will remain unchanged. So 1, 2, 3, 4, 5 carbons across, a methyl group here. And where you had an oxygen as an OH, now it's going to be an aldehyde that was reduced to make the alcohol. So the aldehyde is simply double bond O with the hydrogen over here. And we could put all the rest of these parts in. You could name it if you want. This looks like 1, 2, 3, 4, 5. So pentanal. And it must have a 4-methyl group on it. Well, that seems like a really common use here. That's just coincidence. Okay, so an aldehyde is always going to reduce to make the alcohol, and the ketone is going to make the secondary alcohol, so reduction. Another way of asking this question is what compound would you get if you oxidize it, because you get the same answer. The oxidation of that alcohol will give you the corresponding aldehyde, and the oxidation of this first alcohol gives you the same ketone. Okay, this time we have an alcohol whose name is given, we'll have to come up with a structure. 2-hexanol with a 4-methyl group. So 1, 2, 3, 4, 5, 6. Make sure we leave lots of room. And 2 is where the alcohol group goes. 4 gets a methyl group. Not a big deal. I hope those make sense to you. And then what do we do here? What type of alcohol do we have here? We are looking at a carbon that's connected to 2 other carbons. This must be secondary. And so which compound was reduced to give you this? So let's just say reduction. Well, think about it in 2 different senses, if you will, but it's the same answer you'd get as if you oxidized that alcohol. There's nothing sneaky about it. They really are the reverse. And so you're going to have still 6 carbons. Can't count. And if you start with a secondary alcohol, the product should always be a ketone. Don't make it any trickier than that if you can possibly help it. Remembering that where the oxygen is attached for the alcohol is the same place the ketone has to be. The other parts of the molecule have no part in this process. They will remain unchanged. And so if you could name the initial compound 4-methyl-2-hexanol, the product is going to be very similar. It's going to be 4-methyl, and now it's 2-hexanone. That should make sense to you. Let's hope. Here are some other questions to make you think. The results of these reactions below are going to be what? All right, so you're going to have to decide with this same compound on the left. Let's name it just because we can. 2 carbons as an aldehyde could be called ethanal, or its common name is acetaldehyde. And with a reducing agent, what does an aldehyde turn into? And with an oxidizing agent, what does it turn into? An aldehyde should always turn into a primary alcohol. And the aldehyde, when it's oxidized, should always turn into a carboxylic acid. No trick about it. That's what you're looking for. So I hope that answer number 1 looks correct to you. Not so hard. All right, what else to know about reduction? To make it a quick conversation here, because it seems like we've talked too long already. The reduction reactions of aldehydes and ketones are not just thrown in here for kicks. They're actually going to be used physiologically, to, where aldehydes and ketones are still going to turn into their corresponding primary or secondary alcohols. The reducing agent is going to be a specific biochemical reagent called NADH. It won't be known by anything except its initials typically. And one example of that is this pyruvic acid that turns into a lactic acid. So the reaction here represents something that actually happens every day in your cells, in your body. And this reducing agent in aqueous solutions will turn this compound into a reduced product. So you got to look at it carefully. Pyruvic acid has a ketone, and lactic acid has an alcohol, but this is a secondary alcohol. And if you had to ever remember pyruvic acid, it's an alpha keto. Well, it's a 2-keto acid, but we'll talk about that some other time. I hope that makes some help for you to understand reduction of aldehydes and ketones. They're not as tricky as sometimes we make them. Good luck with your studying. Ask lots of questions, and I'll see you in class.